Go ahead. Oh yeah, it's the same thing. Yes. Yeah. You can just use it in -3 to dash the term. Yeah. So I made a mistake there. Got a little excited. Most of you guys got A. Some of you on B made a small error when you had this -2 times -1 squared plus 4 times -1. You lost the -1 or the -2 when you squared it. So that cost some points. And then the -2 times x plus 4 quantity squared plus 4 times x plus 4. Some things went wrong here. Some of you only put the -2 on the x squared term and didn't distribute that out each of those 3 terms. So this next step, this next steps would be -2. Not working. Quantity x squared plus 8x plus 16. And then plus 4x plus 16. And you have to be careful because the -2 gets distributed to those 3 terms. We talked about number 2 kind of in class, so everyone was pretty straightforward on that. The graph of the function, most of you that had a graph didn't miss anything. It was pretty straightforward. The second graph on the back, some of you forgot what the square root function looked like, but we kind of talked about that in class, so it was pretty straightforward of how that was shifted to the right 3 and up 1. So the graph would be 1, 2, 3, up 1. Here, some of you got close. Some of you tried to smash it down, but the shrink was only in the x direction, not the y direction. So you need to be from -2 to all the way to 2 here, come down here. This point gets transformed there. So if you're transforming each one of these x values, so the old x value is -4, the new x value is -2, but the y value stays the same as it was at -4. You're only changing the x's, not the y's. Here you're doing a combination of things. You have to do the flip first, multiplication before addition. So you flip it first. So just real quick, if you translate each of the dots and then connect the dots, that's the flip. Then the 4 units to the right. So every dot gets shifted 4 units to the right. And I apologize because 4 units kind of took it off the graph paper. So this would be the 4 units to the right. And then 1 unit down. So the new graph will look like this. And most of you that did answer that did that correctly. So I tried to give you guys kind of, each one was worth a point. It was just kind of quick and dirty, easy way to grade it. You know, 9 out of 10, 8 out of 10, 6 out of 10. Not to be too concerned with that score. I want you guys to get more of the feedback, because if you guys do really well on the exam, these scores don't even really matter. So that's what I'm trying to do. As far as on Alex, I'm going to drop the lowest couple. I'm trying to give a lot of in-class quizzes this semester because I think that gives you good feedback. So I'll drop the lowest 1 or 2 depending on how many we give. So if you miss 1 or 2, it's not going to be a huge burden to your grade. Of course, it's in 25% of your Alex grade, which is 20% of your class grade. So again, it's not going to be a huge effect on your overall grade. But if you don't do anything, it can. Any questions on that? I will post the answers to it after class in Blackboard.
The negative indicated the flip, right?
The negative, this negative indicated the flip on the x-axis. And we're going to talk about some today that's going to kind of reaffirm the x-axis and the y-axis. So today we're going to talk about analyzing graphs of functions and piecewise defined functions. We'll talk about test of symmetry. So how do we test to see if this function is symmetric or if this relationship is symmetric? So we're going to get into some relationships. You might remember we defined a function as it passes the vertical line test. Well, if it has x-axis symmetry, it's not going to pass the vertical line test, right? If it's symmetric with the x-axis, it's not going to pass the vertical line test. Things that do that are circles, right? X squared plus y squared equals 0 is a circle centered at 0, 0, right? If this was the y-axis, this would be a circle. That would be reflected about the x-axis. If I fold the x-axis, then the top half of the circle folds over the bottom half of the circle. That's not a function, but it's a relationship. So we're going to deal with a little bit of relationships or functions and then be able to verify, yes, this is symmetric about the x-axis. Yes, it's symmetric about the y-axis. Yes, it's symmetric about the origin. So we'll have 3 types of symmetry. Because something is symmetric about the x-axis doesn't mean it's a function, though. A little bit with the lingo there. So if it's symmetric about the x-axis, that means for every x input, then there's going to be a y or a minus y. Symmetric about the y-axis means for every y output, there's an x or a minus x corresponding to it. Right? So if I graphed x squared, right? If I plug in minus 1 squared, I get 1. If I plug in 1 squared, I get 1. Right? So that's symmetric about the y-axis. So that's saying for every x value, positive and negative, there is a corresponding the exact same y value. Right? So if I plug in positive x, I get y. If I plug in minus x, I get y. The origin is a little bit different. Sorry, guys, I have a couple things open here. There you go. The origin is for every x input, for every x, y input, there's a minus x minus y input. So if I graph something like x cubed, that's symmetric with respect to the origin. Right? 1 cubed is 1, minus 1 cubed is minus 1. So I plug in 1, I get 1. If I plug in minus 1, I get minus 1. So do you guys see that there? It's really easy to tell if something's symmetric with the origin, the x-axis, or the y-axis given a graph. But you're not always given a graph. Sometimes you're given a relationship. And you have to do some plugging in to verify for symmetry. So if we want to test for symmetry, if something is symmetric with the y-axis, what that means is we can replace minus x in the equation. If we substitute minus x for every x, and we get an equivalent equation or equivalent relationship. Then it's symmetric with the y-axis. What this means is f of minus x equals f of x. If it's symmetric with the x-axis, generally this doesn't happen with functions, right? Because if it's symmetric with the x-axis, it's not a function because it doesn't pass the vertical line test. But we can still check for that, and we check for that kind of the same way. If I change y, if everywhere I have a y, I plug in minus y, if I get the same relationship, then I can confirm that it's symmetric with respect to the x-axis. If you can do both x and y to the relationship, then it gets the same relationship. If you plug in minus x everywhere there's an x and minus y everywhere there's a y, and you get the same relationship as you started with, then it's symmetric with respect to the origin. So let's look at these 2 examples here. A. I could graph this, right? I know what the absolute value of x looks like. Looks like this. Is that symmetric with respect to the x-axis? Can I fold that over the x-axis and get? No. Is it symmetric with respect to the origin? No. No. Is it symmetric with respect to the y-axis? Yeah, so we can visually see that with a graph, but we can also see that is if I plug in minus x, right? I have y equals absolute value of minus x, and that gives me absolute value of x. Absolute value of minus x is the same thing as the absolute value of x, which is what I originally started with, right? So this tells me I can replace minus f of x f of minus, and I get f of x. F of minus x, and I get the original function I plugged in. That tells me it's symmetric with respect to the x or y-axis. Right? Symmetry is with respect to the y-axis. So that's part A. What about B? Here, if I plug in minus x, I get a different expression, right? Can you guys see that? If I plug in minus x, then I don't get what I originally started with. But if I plug in minus y, I get what I originally started with. So if I plug in minus y into the function, into the relationship, right? I would have x equals minus y squared minus 4, which is the same thing as x equals y squared minus 4, what I originally started with. So that tells me I'm symmetric with respect to the x-axis. If I was to graph this, it would look like y is 0, x is minus 4. Yeah, it would look like this. This is y squared minus 4. This is the x-axis, and this is the y-axis. It's kind of like thinking x squared minus 4, but rotated 90 degrees, because I'm switching the role of x and y. So this is the graph of y squared minus 4. It's not a function. We don't like to deal with things that aren't functions in college algebra, except in weird cases when we talk about symmetry. So this is symmetric. So we have symmetry here with respect to the x-axis. Do you guys see how you can kind of see that and see if I replace the minus y, I get what I originally started with? So that's going to be, that function is going to be symmetric with respect to the y-axis, or sorry, x-axis. Here, if I replace minus x, then the function is not going to change. So that's going to be symmetric with respect to the y-axis. What about on 2a? Can you see what 2a is going to be symmetric with respect to? The y-axis, right? I know the graph of that function looks like this. Clearly I can see it's, but also I can see if I plug in minus x, it doesn't change the relationship. Everywhere there's an x, if I plug in a minus x, then I'm going to get the same function. Eventually we're going to talk about odd functions and even functions. Even functions are symmetric with the y-axis, and odd functions are symmetric with the origin. So we'll talk about polynomials that act certain ways. What about on B? The x-axis, right? Can you kind of see if I replaced minus y, that doesn't affect the equation or the relationship. But if I replace minus x, it would. It wouldn't be the same. Kind of see that? This graph looks like trying to think, this graph would look like this, which wouldn't be a function. We don't like to deal with things that aren't functions, but this is symmetric with the x-axis. Okay, see that? Here's some graphs. Eventually we're going to get to some graphs. This is a graph of x squared plus y squared equals 9, which is a circle centered at 0, 0 with radius 3. You guys familiar with some kind of those notation? In chapter 7, the very last couple of weeks of the semester, we'll go into different graphs of functions, hyperbolas, hyperbolas, and hyperbolic graphs, and we'll talk about the shifts in the general form. But here, if we want to talk about symmetry, this is symmetric with respect to the y-axis, the x-axis, and the origin, right? For every 0.22, there's a minus 2, minus 2. A way to show that is if I replace x, if I replace that with minus x, I still get x squared plus y squared equals 9, right? Because minus x squared is x squared. If we replace y with minus y, I still get x squared plus y squared equals 9. I get the same thing. If you can do both, it's symmetric with respect to the origin. Right? So this would be the y-axis. This would be the symmetry. X-axis, origin.
Okay, so you replace it with the, if you replace the x with the minus x, that's the y symmetry.
Yes.
And then, okay.
The x, yes.
Okay.
And that's typically what we look at when we talk about functions, because we won't really talk about changing y to minus y, because that would be an x-axis symmetry, and that wouldn't be a function.
Okay.
Right? This is not a function in the sense it fails a vertical line test. In functions later on in math, like in calculus, there's certain things, it has to be a function for a derivative to exist. So to be able to talk about a slope, you have to have a function, because here at this minus 2, it has two different slopes. So it's not a function. So we can't talk about, a lot of times we'll have to limit the domain to be maybe this relationship. That's a function. Then I can talk about the slope at minus 2. But I can't talk about it unless it meets the condition it's a function. That happens later on.
You said that would be an origin?
This would be both too. It would be all three. Yeah, it's the y-axis, the x-axis, and the origin.
So both is never a function either, right?
No, it could be like x cubed.
Okay.
X cubed would be the origin, because if you have to plug in both x and both. So let's just real quick, look at y equals x cubed, right? If I plug in minus x everywhere there's an x and minus y everywhere there's a y, I have minus y equals minus, oh, that's a cubed. Minus x cubed, right? So that gives me minus y equals minus x cubed, which gives me y equals x cubed. So that's the original function. Oh my goodness, what is wrong with me today? Cubed. I like the squares. So you see how if I do it to both of them, I get the original function. So this would be symmetric about the origin. So this graph would look like this, but it's not symmetric with the y. Because if I just do the y, I get minus. If I just do the x with a negative x, I still get a negative. But if I do both, I get symmetric with the origin. Here, it's because when I do both, x goes to minus x and y goes to minus y, I end up with the same relationship, x squared plus y squared is 9. So this is symmetric with the x-axis, the y-axis, and the origin.
So it's not always going to be the case.
But it's not always the case.
Okay.
If it's symmetric with the origin, that doesn't mean it's symmetric with the x-axis or the y-axis.
Okay.
Like this case here, this is only symmetric with the origin. And sometimes algebraically, it's a little harder to see than visually. Right? And we'll get in, where this really comes in handy is even in odd functions where they're in behavior, because we'll talk about graphing. If we know the function is overall odd, it's going to act a certain way. If we know it's overall even, it's going to act a certain way. So being able to classify a function as odd or even comes in handy. So an even function is going to meet the requirements that it's symmetric with respect to the y-axis. That means if I plug in minus x, I get out the original function. And if you can kind of see here visually, if I plug in 1, I get out 3. If I plug in minus 1, I still get out 3. Right? If I plug in 3, I get out 0. If I plug in minus 3, I get 0. You can also think of that if you kind of fold that over long ways, then this dotted line is going to match up with this dotted line. The graph is going to mirror itself. Right? So that's what an even function does. An odd function is symmetric with respect to the origin. So everywhere I plug in a minus x, I get out minus y in a sense, minus f of x. Y is f of x, right? Y is f of x. So here I plug in 2. Let's plug in maybe 1. If I plug in 1, I get out 1. So if I plug in minus 1, I should get out minus 1, right? Minus x equals minus y in a case. If I plug in positive x, or if I plug in x, I get out a positive y. If I plug in minus x, I should get out a minus y. That same value though, right? If this was 3, 1 point, whatever this is, 1.3 maybe. So if I plug in minus 3, this is going to be minus 1.3. You guys see that? So this verifies it's symmetric with respect to the origin. This is symmetric with respect to the y-axis, tells me this is an even function. This is symmetric with respect to the origin, that tells me it's an odd function. The instructions here is to label them as even, odd, or neither. You guys see that? Just visually looking at the picture saying that's an even function. Looking at the picture, it's an odd. It's odd, right? Symmetric with respect to the origin. If I plug in 2, I get out 3. If I plug in minus 2, I get out minus 3. If I plug in 3, I get out minus 2. If I plug in minus 3, I get out positive 2. You just kind of see that? What about this one? Neither, right? Neither is a choice. And the last one, even. I plug in 1, I get out 2. I plug in minus 1, I get out positive 2. Of course, we don't always get these nice, pretty little graphs. This is called college algebra, so you might have to do algebra. So a way to check it is if f of minus x equals f of x, you get an even function. And the easiest way to remember, x squared is even. So if I plug in minus x, I get x squared. I get the original function. If I plug in f of minus x and I get minus f of x, this is odd. Right? If I plug in and I get nothing interesting, something different, then it's neither. Huh?
It's definitely Monday.
It is definitely Monday. That is for sure. All right, for A, can you guys kind of see if I plug in f of minus x? I'd have minus 2 times the quantity minus x to the 4th power plus 5, the absolute value of minus x. Simplifying that, minus 2 stays the same. Minus x to the 4th power can be written as x to the 4th plus 5, absolute value of x. Is this the exact same thing as the function? So this equals the function, so this tells me it's even, right? It's an even function. If I plug in the minus version of x, I'm going to output the same thing as if I plug in the positive version of x. Question?
You've got absolute value of x.
Mm-hmm.
Does that pretty much give you a hint there? That it's
Kind
gonna
of,
be-
and in also even powers.
Right.
Yes, and odd powers are going to kind of play the same thing, but you got to be careful. There's different things. Like on C, we got an even power and an odd power. So this is going to be neither. But on B, we have 2 odd powers, right? So it turns out it's actually odd. And that's going to be something we're going to be able to use, right? But if this then had like plus absolute value of x, it'd be neither. So yeah, just the algebra here, if I plug in minus x, I have 4 times minus x cubed minus x. That tells me that's 4 minus 4x cubed plus x, which I could write as minus 4x cubed minus x, which is exactly minus f of x.
So when we use that the power, if one's even and one's odd, is it always going to be even?
If one's even and one's odd, it's always going to be neither.
Or is it neither?
Yes. So this example, because 1 is odd. So if I plug in minus x here, I have 2 minus x squared plus minus x, which is 2x squared minus x, which is not the same. Or if I pull out a negative, that's going to be minus 2x squared plus x, which is not the same what I originally started with. But here, if I pull out a negative, it is the exact same. It's negative of what I started with. So that's odd. Yeah, so here, basically, if you can say at any given term, if I can plug in minus x and get the same term, it's going to be even. But you have to do that to every term, right? So here, I can plug in minus x is the same, minus x is the same, so that's even. Here, if I plug in minus x, I get minus the term. Here, if I plug in minus x, I get minus the term. So then that's going to be odd if I can do that every time. Here, I plug in minus x, I get the term. But if I plug in minus x here, I get minus the term. So that's why this one's neither. Yeah, it only takes one term to throw it up, to mess it up. But eventually, we'll be using it to be able to classify the highest term. And then that's going to tell us the end behavior. Is it overall going to act like an even one and go both up? Because even in the end are going to be both going up or both going down, depending on the leading coefficient. We kind of look at a graph here. Even if the end behavior is going to go both up or both down, but it has to be the same. And then odd, one's going to go up and one's going to go down. Depending on the leading coefficient, we'll discuss how that works. But at this point, we're just classifying as even, odd, or neither, or symmetric with the x-axis, symmetric with the y-axis, or symmetric with the origin. The next thing we talk about is kind of, again, more notation. Graph the piecewise defined function. So they give you a piecewise defined function, and they also give you the graph, and they have you evaluate it at 4 points. I think the graph is very handy here. If I plug in minus 3, I can see that I'm outputting as 2, right? X at minus 3 is 2. But you should be able to do it algebraically. So a lot of times what I'll end up doing is I'll kind of draw a number line from minus 4 to minus 1, including minus 4, but not including 1. The value of my function is going to be evaluated using minus x minus 1. From minus 1 to 2, including minus 1, but not including 2, if I evaluate my function anywhere in that region, I'm going to output to minus 3. Right? That's what this is saying. And then from 2 on, it's going to be the square root of x minus 2. So if I want to know what f of minus 3 is, minus 3 falls within this region. So I take minus 3 minus 1, and that's going to give me, oops, didn't write that right, minus 3 minus 1. And that gives me 2, which graphically comes up with the same. Do you guys recall piecewise defined functions? We're going to do 2 things with a piecewise defined function. We're going to evaluate it at a certain point, and we're also going to graph basic constant and linear or maybe even quadratic terms within there. So if you were given this piecewise defined function, could you have come up with this graph? So that's, so, I mean, part of it is exposure. If you're seeing it for the first time, it's going to take some time. If you do it 500 times, it's going to probably take a little less time. What this is saying is from minus 4 to minus 1, the function has a relationship minus x minus 1. You can always plug in points. That's a great thing about graphing sometimes. If I plug in minus 4, so minus a minus 4 plus 1 tells me my output's 3. So that point's there. I know it's a line. So to draw a line, I need 2 points. I need 2 endpoints, right? So if I plug in minus 1, the strictly less than tells me it's going to be an open circle. If I plug in minus 1, I have minus, minus 1, minus 1. A little bit careful there, right? So a minus minus 1 is a positive 1, plus the -1 gives you 0. So I have an open circle here. So if I connect this line between these two dots, I have the graph that represents from -4 to -1. Now I go to my drop. If I am -1, my output is 3. So that tells me is -3. If I'm -1, my output's -3. So that tells me I have a closed circle there. If I'm anywhere between -1 and 2, open circle here, I'm going to be -3. So that's a constant function. So I connect those two dots. If I am 2, I plug 2 into this function, the square root of x minus 2. So that would be the square root of 0. So if I'm 2, I close circle at 2, 0. And then I get the square root function, right? Square root function shifted to the right 2 units. And then I just connect that out. Evaluating it, if I want to evaluate it at -1, f of -1, what interval am I looking at? I'm looking at the interval including -1, so everything that outputs there is -3. You guys see that from the algebraic expression of the piecewise defined function? The -1 tells me I'm in this interval. What is a function evaluated this interval? It's always -3. From -1 to 2, it's always going to output to -3. What about f of 2? This is going to be 0, right? Because I have 2 minus 2, that gives me 0. What about f of 6? It's going to be the square root of 6 minus 2, which is the square root of 4, which is 2. So do you guys see that? It also corresponds to the graph. If I look at f of 2, that tells me my answer here is 0. Because I have a closed circle at 0 and an open circle down here. So at 2, my output's 0. At -1, my output is -3. At 6, my output would be 2. At -3, my output would be +2. So you guys see how the graph also can give you a way to represent the value of the function at a point. And that's all kind of what you're doing, is you're finding the interesting points in the piecewise defined function. If you're asked to graph it, you're going to be finding the interesting points and then connecting them with lines. Either it's a line with a positive slope or a negative slope, or a slope of 0, meaning it's constant. Look at this next example. It's going to just evaluate the piecewise defined function. So we don't have to graph it. What would be the piecewise defined function? How would it be defined at plugging in -3? 4, right? So the -3 tells me I'm in this region. X is less than -2. So I plug in -3 into this relationship. So -3 plus 7, and that gives me 4. What about at -2? So -2 tells me I'm taking -2 squared, and that gives me 4. At 1, 3. And what about at 4? 3. So now that I've kind of done this, graphing it should be pretty straightforward. If I'm less than -2, also let's go to -2. At -2, I know I'm 4. My output's 4. But if I'm less than -2, I'm a line with slope 1. I have a positive slope, right? So if x is -7, then it'd be 0. So this would be -7. So this is just a slope of 1, right? If I was to graph that. You could go ahead and say, well, what is -3? Oh, -3 was 4. -3 was 4, right? -2, what would -2 be if it was following this line? It'd be 5, right? But it doesn't follow the line, so it'd be open. But in between -3 and -2, it does follow that line. So at -2, it's open at 5, but closed at 4. Right? F of minus 3 is 4. F of minus 2 is also 4. But in between minus 3 and minus 4, I'm still going up, approaching. If I would have plugged minus 2 into this function, it would be 5, but it's an open circle because this is strictly less than. You guys see that? From minus 2 to 1, I follow a quadratic, right? So it would be open at the endpoint, but the general graph is quadratic. I didn't do any more work except know how to graph a quadratic in that region. And then from 1 to 4, I output at 3. So I have a closed circle here and a closed circle here, and that's a constant function.
So how did you know C was the
Here,
Oh,
because I'm following that. So I know this is a line with a positive slope, right? And I can draw a line with a positive slope if I have 2 points. I can plug in another point there and get that pretty easy. And I know its rise over run is 1. So I go up 1 over 1, up 1 over 1. It doesn't matter that my y-intercept is plus 7 because I don't even get anywhere close to the y-intercept. I only graph it in this region. And then for the second region, kind of like you're saying, I know that this is an endpoint and it's closed, and I know this is the endpoint that's open. If I plug in 1, I get 1. But it's open because it doesn't include 1. So then I know I connect them with a quadratic or with that kind of function. Then here, connect them with a constant. Does that make sense?
Yeah,
So by doing all this work, I get the graph pretty easy. Sometimes it's overwhelming though, when it's like graph this, it's like, you only have to look at the critical points though. You look at minus 2, maybe minus 3, minus 2, 1, and 4. Once you get those points on the graph, you just kind of connect them with the relationship of the function. If it's a line, a quadratic, or a constant, it won't be anything other than those, right? So what about graphing this piecewise defined function? X is less than 1. I have a line with a negative slope of 3. So fall 3 to the right 1, or I can go up 3 and to the left 1. Because it's the rise over run 3. Does that make sense? You guys remember that from 050, 040, 110? I'm not sure exactly where that slope, rise over run though. So this is just a line. It goes through 0, 0, but if I was to graph this, I'm going to say, okay, x equals 1. That's kind of where it switches over. If I plug in 1, my value of the function is minus 3. Turns out if I plug in 1 here, the value of the function is also minus 3. If I plug in 0, the value of the function is 0. So this is actually just a line that has a negative slope that just keeps going. Once you have 2 points, you just connect those 2 points and extend that line out. And then this is telling me it's a constant minus 3 for everything else. This happens to be a piecewise defined function that's continuous. There's no discontinuity. There's no jumps. Look at the next one. Very similar to the kind of one we did before with an x squared and then an x plus 3. So looking at maybe minus 1, minus 2, 1, and 2. For x that's less than minus 1, it's going to be this function. So if I plug in minus 1 here, minus 1 plus 3, so minus 1 plus 3 is minus positive 2. Sorry, minus 1 plus 3 is a positive 2. So that's an open circle because it means it doesn't include minus 1. My slope is still positive 1 though, but if I plug in minus 2 plus 3, gives me a positive 1, right? So all I need is 2 points. Connect those 2 points and go. My scale's a little off. This would be minus 3. Question?
I'm just, where's this? How are we getting the open circle?
The open circle is because this is, it doesn't include minus 1, but it's saying everything up to minus 1. X is less than minus 1. It's not equal to. The closed circle comes through when it's equal to. So if I plug minus 1 in here, I have minus 1 squared, which is a positive 1. So this would be the closed circle at minus 1, 1. Right?
I get how we get a negative 1 on the x-axis, but how are we going up or down the y-axis?
Oh, that's a good question. So here, if I plug in minus 1, I'm just pretending to plug it in this function because I'm going to put an open arrow, an open circle there, right? I know this is a line. I have to graph this line, and it's going to be a line all the way up into this point x equals minus 1. But I want to know what point I'm going to because I need 2 points to connect the dots, right? So if I plugged in minus 1 plus 3 would be 2. So my output is at 2. That's an open circle that way. It means as I'm getting closer and closer to minus 1, I'm getting closer and closer to this dot, but I never hit that dot. Right? And then if I plug in minus 2, I get 1. If I plug in minus 3, I get 0. So since I have these dots, I can just connect them to get a line. To draw a straight line, all you need is 2 dots. And if you put them a little bit further apart, it's easy, a little bit easier to kind of extend that. So now if I plug in 2, I get 4. And that's an open circle, but then that's still a quadratic. Open and closed circles are important on piecewise defined functions. Because now if I say, what is the value at minus 1? The value at minus 1 is 1. What is f of 2? Again, with the does not exist. I'm going to go ahead and pass around the sign-in sheet before we run out of time. Because 2 is an open circle there.
You could just pick any points basically, right?
Yeah, you can, and you want to pick the interesting points, right, where it's transitioning. So at minus 1, it's interesting because something's doing different. From any point on the left of minus 1, it's a line. So if you get 2 of those and connect it, and you want to kind of connect the interesting one to what it goes to the open circles. So you want to find the open circles and the closed circles, and then say, okay, this is a line, this is a quadratic. Maybe this I could add 1 if x is greater than 2 or equal to 2, then this would be that. So you want to look at what region you're in and go from there. If I want to continue on here. The last part of this section is notation, really, being able to write an interval notation. So you're going to be asked, on what interval is this function increasing? Right? It's only increasing on this interval, right? Decreasing, constant, increasing here, and then decreasing again. So it's increasing from 2 to 3. Everywhere else, the function's decreasing. So where's the function decreasing at? Right? It's decreasing from minus 4 to minus 2. It's running constant here, so I don't write that interval, and then 3 to infinity. So one way to write that is with a union. This might come up in Alex. So decreasing from minus 4 to minus 1, union 3 to infinity. So you only ever put the x-axis, the x inputs. If I plug in minus 4 to minus 1, my function is decreasing. And then from 3 to infinity, it's still decreasing.
Why is it that minus 1?
Because at minus 1, it stops decreasing.
Oh, you wouldn't put minus 2 though.
No.
It's the.
Are you talking about this? This is the value of the function at that point. But for increasing and decreasing functions, you only look at the domain, right? I'm decreasing here and here, right? I'm increasing here, and I'm constant make it even longer. I'm constant from -1 to 3. So I'm constant at from -1 to 3. Huh?
-1 to 2.
-1 to 2. Thank you. -1 to 2. Question.
The close dot, does that not change how you move?
So I believe in Alex will say an open interval. So they want you to put open in everything. Technically, increasing, we have to have something to compare it to. So it can't be increasing, decreasing, or constant at one point. So this is the exact same set as this. Because 2, you can't talk about it increasing, decreasing at 2. You can only talk about it from 2 to a little bit to the right of 2 or a little bit to the left of 2. So on Alex, I think it'll even say use open intervals. So
what A do we use a bar or a
bracket,
bracket? Yeah.
you use an open parenthesis on Alex. It'll tell you use open intervals because you can't be increasing, decreasing, or constant at any given point. You have to have something to compare it to, right? So the domain includes -4, but you're increasing or decreasing from -4 to -1. So we'll do the last little bit on maximum minimums. It's pretty straightforward though. Where does the maximum happen? What's the value of the maximum? We'll talk about that next time.